Hello viewers, today we will use multiple indicator cluster surveys to do some basic regression analysis. I made some videos on merging data sets of multiple indicator cluster surveys for Pakistan, province Punjab, and I got some requests from some of the viewers that they wanted me to make a video on, or make series of videos on regression analysis using these data sets. So this is first of the series. So I'm going to use the same data sets that I used for merging videos, and I'm going to do some basic regression analysis on them. So what I've done already is that I have the child data set, as you can see right here. It's a child data set, and I have already merged it with M:1 with the household data set. I have explained it in detail in other videos about what these M:1 means and so on and so forth. So if you don't know them, if you want to learn about them, I highly recommend that you go to the description of this video and watch those videos. So what we have right now is the merged data set of child and household data, and this is the merging outcome table, which tells us that from using, we have 28,982 households that did not have any child, because household data was our using data right here, right? So in using data, there are 28,982 households where they did not have eligible children for data. Simply, in simple words, these households are not useful for us. So what we can do is we can drop these households, drop if underscore merge double equal to 2. So this is dropped, and we can also drop the underscore merge if we want. Drop underscore merge variable. All right. So what do we want? Let's say that we want something to do with stunting. Stunting is the variable that is commonly used to measure the malnourishment of children in any country. So if a child is shorter than normal child of his or her age, then we say that the child is stunted or has stunted growth. And this is a serious problem because it has long-term consequences for the productivity of an individual. And since the combination or like collection of individuals make up societies and countries, if there are many of such individuals who are not growing up to their potential, it means that their growth will be retarded. The country's growth will be retarded. Most common indicator that we use to measure stunting is height for age. Let's see in this data set, I will write height here, and I can see that there are several variables related to height. What we need is height for age z-score, height for age z-score, which is HAZ. So since WHO's HAZ variable is the most commonly used one, we are going to use that, and we will see some of the summary statistics of this. Sum HAZ2. So what I have is I have minus 5.9 and we have 99.99. So the criteria through which we judge whether a child is stunted or not is the value of these z-scores. So these z-scores range from -6 to +6. So you can see that -6 is fine, it's minus 5.9, very close to 6. But instead of +6, we have this strange 99.9, right? So we have to see what is going on. So what we can do is we can tabulate HAZ. It will give us a long list of HAZ scores, but we can have a look. If I keep pressing the space bar, I can reach the end very quickly. And I can see that the actual largest value is 5.96, but I have these strange numbers right here. Most often, if you see strange numbers like this in data sets like multiple indicator cluster surveys or demographic and health surveys, it means that these values are not reliable, or there are some flags associated with it. What flag means is that even though the enumerators who collected the data, they provided some statistics, But when this data was cleaned, the analysts thought that, okay, this value is not really reliable, so they flag it. Usually they mark these kind of indicators with these numbers, and it means that if you want to use this variable for some kind of analysis, you have to drop these values because they are not useful. But there is usually some value, some number attached to it, some label attached to it. Let's see if there is some label. So I'm going to try label list HAZ2. We do not have any label like this. We have HAZ flag right here, right? So let's try to tap that. So we have no error or error flags. So let's see if I sum them up, right? I might get this number. If I sum this up, 17 plus 583 plus 1152 is 1752. And this is right here. So HAZ flag, this additional variable, is telling us that all these three types of numbers that we have, they are reflecting some kind of error. So what do we need? Now we need to drop all these variables, all these values that are incorrect, right? So we have a clean HAZ2 variable. I could call it gen height for age z score 3, okay, and I am calling it HAZ2. Right, so I have this new variable, and I can replace HAZ3 equal to dot if HAZ2 is greater than 6, because we know that if the value is greater than 6 here, it means that there is an error. So anything that is, we have 99 something which is greater than 6, so this seems to be a safe formula, and this should change 1752 observations, right? Let's see what happens. So it does change 1752 observations. Now if I'm going to sum HAZ3, I get minimum value of minus 5.99, maximum value of 5.96. Okay, so far so good. Now I need to define whether a child is stunted or not. Okay, so in order to know whether a child is stunted or not, we have standard classifications, standard definitions by WHO and other organizations that tell us whether a child is stunted or not, which is based on these indicators right here. So this is a table from the same data set, multiple indicator cluster survey, and I am taking this table TC 8.1 as an example, and you can see here is that using height for age that we are using right now, they have created two types of variables. One is -2 standard deviation. If a child falls below, if the height for age z score of a child falls below -2 standard deviations, it means that the child is moderately or severely stunted, right? That is the definition of WHO. And if a child falls below -3 standard deviation, which is much more severe than -2, then a child is considered to be severely stunted, right? So these are the criteria, the definitions that we have to account for when we are calculating the percentage of stunted children in the data set that we are using. So what we have here is that these are, so this is we have the data set. We can also see the histogram of this. So we have this histogram, and we have a 0 here, -5 here, so -2.5 should be somewhere around here, -2 should be somewhere around here. It means that any child which is below this category, this bar right here, assuming that this is -2, the children who are below this range in this area, they are moderately and severely stunted. If -3 is around here, it means that children who are below this area, if they are here, on the left side of this area, then they are severely stunted. So we have to use this criteria to define a variable that takes the value of 1 when the child is moderately stunted or severely stunted, using the criteria of -2 standard deviation and 0 otherwise, right? So we can use the command called recode, and we could recode the value at the variable HAZ3. So what recode does is that it is a kind of a better version of replacing. We did some replacing right here, right? So if you have multiple criteria to create a new variable based on an old variable, then it is better to use recode rather than replace command. You can do the same thing with replace as well, but you have to do it in 3 or 4 steps. You can do the entire exercise in 1 step if you use recode. So if HAZ is between -6, because we know that the minimum is -5.999, so -6 is the lowest we can get. Between this and -2, then we say that call this child stunted, which is equal to 1. Otherwise, if the value is between, let's say, -2.001 to include any possible values to 6, it is 6 is greater than 5.96, so just want to include everything, then the child is not stunted, right? And okay, and if I just do this, it means that the STATA will change all the values inside HAZ3 and replace the values here. I don't want that. I want to create a new variable based on this criteria, which will be called stunting. Okay. Or I could actually say moderate, severe, stunt. So it is moderate or severe stunting. Okay. Now I can tab this MS stunt to see if what we created made sense. So we saw in the report that moderately stunted children are 31.5%, and this is what we are seeing here as well, 31.8%. That is because we did not assign weights here. We have to assign weights because this is a sample data. So what we can do is we can go here and we can assign some weights here. Here we can go to sample. If I write sample here, it tells us child under 5 sample weight. So I can use this right here, and I click enter, and you can see that the number has slightly decreased. Even though we have child weight in the data set, for accurate measurement of the percentage of children who are stunted, we have to multiply the child weight with the number of members in the household. The number of members in the households is this HH48. What we have done here is that we have created a new variable called weight, and we have multiplied the child weight with HH48. So this gives us a new type of weight, and we use the same this way to tabulate MS stunt. What we get is 31.5, which is exactly the same as the number we get here in the mix report. So we can be sure that what we have done here is fine, right? So this is the stunting variable. You can create the same, you can use the same kind of command to create severely stunted also. So for severely stunted, our criteria is -3. We use that. Here we change it to 3 as well. And instead of moderately and severely, we say severely stunted. Here we go. And we also tabulated using our new weight. And this tells us that 11.49% children are severely stunted in Punjab. So is this true? Yes, 11.5, right? So far so good. We are done with the stunting variable. Now, What we want to do, our hypothesis, let's say, for our regression analysis is that mother's education and water supply in the household matters for childhood stunting. Right? There are many variables that can matter, but for this analysis, for this exercise, we are only concerned about mother's education and water supply type of the household. So what is mother's education? Let's see. Mother's education level is right here, and let's tab it and see if there are some problems with this. I think we don't have any problems here because we do not have those strange values like 99 or something like that. That seems to be okay. And we need water supply, right? Water, here we have main source of drinking water. Let's tab it. We have all these types of water supply. And if I include this, we have non-responses as well. If I include this variable like this in the regression, it will not make much sense, right? I need to, there is a definition of improved and unimproved water source by WHO and World Bank and UNICEF. We could use that. So what we can do is I can recode. First, I have to look at the scheme of labeling in this one. So the name of the variable is WS1. I want to see, these are the labels right here. I want to see what are the numbers behind these labels. For that, I need to see the labels assigned to this variable. I type label list and I type WS1 and I get this list, right? So if there is the value of this WS1 variable is 11, then the label assigned to it is this one. So I can use this whole scheme to create my new variable, which will be improved water. So I have this table right here, which should tell us which kind of water sources are improved, which are not. So from this, I can see that from here to here, we have unimproved water sources. And from here to all the way here, we have improved water sources. So the only ones that are unimproved are unprotected well, unprotected spring, surface water, and others. These are the unimproved water sources. The rest are improved water sources. So we can use this criteria to generate our new water variable. Or instead of generating, I could recode WS1, and I want to say that if it is 11, 12, 13, I'm looking at these categories right here. Or if it is all in series like 11, 12, 13, 14, I could also say 11 to 14. So everything in between also counts, is considered improved. Then I give a space. I say 21 to actually 31. 21 to 31 is also improved. 32 is not because it's unprotected well. Then 41 is fine for us because it's protected spring. Rainwater is okay, provided that it is treated correctly. Then we have tanker truck. This is 61. Then we have cart 71. Then we have water kiosk 72. And then we saw that surface water was also considered unimproved, so we will not include that. Packaged water like bottled water is also included, so 91. Okay, so all this we are saying that these are improved, so it's equal to 1. And the other ones that we did not include will be 32 right here, unprotected well, 42 unprotected spring, and then we have what, surface water 81. This is equal to 0. And we do not have any other, so we are just leaving that out. Gen, we are saying Gen, let's say improved water. imp water. Okay, let's see what happens. Now let's try to tab improved water. We have these 96 and 99 as well, right? So these 96 and 99 we did not, okay, so it was not showing up. So 96 had to be included as well. Okay, so let's do this again. Let's drop this, drop imp water. These kind of mistakes happen, so I'm doing it together with you. So if this happens with you, that's completely fine. So others is considered, other is 96 and it is considered unimproved as well. And we are saying that we have no response for people who had 99. So we have like 7 households that had no response and we want to exclude them. So we say that if it is 99, then you give it a dot, and when we close it, okay, now let's see, now it should work. Okay, page up, let's press page up, this one, tab improve water. Now it's fine, 96.35. and if I do this, if I do this with weights, that should be okay. So now this variable is correct. Now we have stunting, we have mother's education, now we have also improved water. How do I run a regression here? So because my dependent variable here is stunting. So stunting, the way I created stunting is, let's see again, tab, what was moderately and severely stunted is 0 and 1. And if your dependent variable is 0 and 1, you have to use Logit or Probit, right? Usually we use Logit. We have to look at the distribution of the data. If it is following similar to normal distribution, then you go for Probit. If it is following similar to logistic distribution of data, you go for Logit, right? So generally you'll see in many papers that for regressions like this, they use Logit. So I'm going to use that, Logit. Dependent variable is moderately severely stunted. Independent variable is improved water. And I'm saying that mother's education is also my independent variable. So what was mother's education? Mother's education level, this one, double click, this should show up here. And I could run this now and see what happens. So I have this finding, it says that stunting increases, so that is something troubling. Improve water, I will explain this to you in a minute. This shows us that mother's education level, when mother's education level increases, then the chances of a child getting, likelihood of a child getting stunted decreases. Okay, and here it says that if a household has improved water, the chances of getting stunted is higher. The reason behind it is a little bit more detailed, maybe beyond the scope of this video, but I will explain it to you because I've done some papers on it, some research on it with the World Bank as well. So the reason behind it is that, remember, the way we created improved water, we included pipe water as well as motorized pumps and etc. in improved category, right? But improved, the definition of improved assumes that the water sources that are counted in improved water, they are free from contamination. They are free from bacteriological and chemical contamination. However, what we have seen in Pakistan, especially in Punjab, for which this data is being used right now in this video, what we have seen is that pipe water is not really safe. Actually, it has more bacteriological contamination than unimproved sources. So this is why we can see that improved water is positive and significant. Having said that, when we increase the number of independent variables in the model, when the model fit starts to improve, right now our model fit is pseudo R square is 0.4, meaning 4% of the variation in stunting is captured by these two variables, which means that 96% is captured by something else, which indicates that the model is far from complete. So we have to include many other variables like child's age, child's gender, the locality, wealth status, many other things. But the objective behind this exercise is not to define the complete model for stunting, but to show you how to run some regressions, right? So we'll keep it simple this way. Also, I have not defined the weights for the sample. We have to account for the weights also in this regression framework, otherwise the findings are going to be imprecise. So before we do that, these are the coefficients. In logistic regression, we have coefficients like positive and negative. We can also have coefficients in the odds ratios. Like if I define comma OR, then this will be odds ratio. How to interpret odds ratio? It is actually, if you see these p-values, they are exactly the same. The only difference is that these coefficients are now transformed into odds ratios, and when this value is greater than 1, like it is right here, it means that when we have improved water, the likelihood of getting stunted is higher. The interpretation of the coefficient becomes positive, like positive correlation between independent and dependent variable when odds ratio is greater than 1. When odds ratio is less than 1, like it is right here 0.7, it means that the likelihood of getting stunted is less when mother's education level increases, meaning that there is an inverse relationship between these two variables. So to incorporate the sample weights in this analysis, we have to use survey set. So I have to use this command, for which survey set contains these different inputs. The first one is you have to put PSU here, primary sampling units, or in this case we have cluster number is the same thing. So you put HH1 here because it's the primary sampling unit here. Then we have to assign probability weight. That is the weight variable we created using child weight above, if you remember, here, right? So this is the same, okay? This one, and strata, the stratification in the sampling design of mix is done using area, which is rural urban. So this is why we use HH6. HH6 represents area. And then we have this single unit certainty is a little bit more advanced. We'll not go into detail. So we'll define survey set like this. Now it is defined. And next, when we run the logit, we have to define SVY before, and then we run this regression, right? So the coefficients will be slightly different now as compared to what we did before. So again, I will run this one again. You can see that this variable was significant. It was 1.22 and it was significant. Now after incorporating the sampling weights, the coefficients odds ratios are the same, but the significance has changed. So you can see that the p-values or significance has changed after you include the survey set with the regression command, right? So this one is insignificant. So there is a little bit more weight on the standard errors when you include the survey weights, and this is what we have to do when you are using survey data set, right? So this is how you can do a very basic regression analysis using this. Before I sign off, I also want you to show that it is not necessary that you only use stunting variable like 0, 1. What happens when you truncate a variable like this, convert a continuous variable into 0 and 1, you lose a lot of information, and that can affect your final outcomes. So instead of this logit, another thing you could do is you could use simple OLS on that HAZ3 variable that we created. Why I'm using HAZ3? Because remember, HAZ2 had those 99 point something those flag observations that I don't want to include in my regression. And of course we don't have odds ratios in the simple OLS regression. So but still I will use SPY, and I can use, instead of using stunting 0-1, I could actually use HAZ3, meaning height for age z-score. What it is looking here is that whether improved water has a positive relationship with child's height in terms of height for age z-score, and whether mother's education level, when mother's education level increases, does it also increase the height of the child. So it does not tell us anything about stunted or not, but it does tell us about whether a child will be taller or not, right? So we can run that, and we can see that this one is insignificant. So if this is insignificant, it means that we don't have to interpret it. It is statistically equal to 0. Here we can see that there is a positive sign. This is not an odds ratio anymore. Remember, this is a standard deviation because our dependent variable is in standard deviation form. So we can see clearly that when mother's education level increases, the height for a z-score of a child also increases. So there is a positive relationship between mother's education level and height of the child. So it means that when mothers are educated, they are better equipped or better able to take care of their children. They feed them better, they take care of them better, and this is why their children are taller than the other children. So thank you for watching, and if you want me to make more videos on these kind of topics, give me some research questions that you want to address. If it is possible using these kind of data sets or the data sets that I have access to, I'll make a video for you, and it will be my pleasure. Thank you so much.